Good evening, students. This is Mr. Rich for another Sunday night Q&A. It's 8 o'clock, a little bit after 8 o'clock now, actually. And we've got some questions that have come in on AP Calculus, so we are going to get right to those. I hope you've had a good 5 days off as we were spared the brunt of the storm that came through Florida. And you all are going back to school on Tuesday. Let's take a look at what we've got in AP Calc. Here we go. First question is, what is the slope of the line tangent to the curve y cubed minus xy squared plus x to the third equals 5 at the point 1, 2? So let's take a look at that. Let's move this thing out of the way. Well, if I'm going to get the slope of a line that's tangent to a curve, my goal is to find dy dx. That's what I have to do. And to find dy dx, I'm going to have to implicitly take the derivative of this curve. So that's my job. I got to get a dy dx. And in order for us to find dy dx for this, we're going to have to use, it looks like the product rule, because I do have the product of two functions in that term. I'm also going to have to use the chain rule because I'm taking the derivative of a variable that is not x, right? This dy dx says I'm taking the derivative of y with respect to x. Anytime, therefore, I'm taking the derivative of my variable y, I need to, by the chain rule, add a dy dx into the derivative process. So I'll show you that as we go through. Once I'm able to get the derivative, I can then evaluate for dy dx at the point 1, 2. Well, here's what we're going to do. We're actually going to start this process by taking the derivative with respect to x on both sides of the equation. So in that sense, it's like an algebra move where we are doing the same operation on both sides. Well, the operation on the right-hand side is going to yield a 0 because when you take the derivative of a constant, you do get 0. But now what we have to do is take the derivative term by term of these three terms on the left. Well, the derivative of y to the third is going to be 3y squared, but times dy dx, right? That dy dx, again, is added because of the chain rule, because the inside part that I'm taking the derivative of is y, it's not x. And therefore, I need to multiply by its derivative, by the chain rule. And the derivative of y is dy dx. Now, when I move to the derivative of this next term, I have to recognize that this is product rule along with the chain rule with the y squared mixed in. But look what I'm going to do, right? In order for me to do this, I want to do this without using a lot of parentheses and getting confused with the sign. So what I'm going to do is the negative x, I'm going to define that as my f function and the y squared as my second function, g, in terms of the application of the product rule. Because the product rule, I'll write the formula down that I'm about to use. The product rule that I'm using here is that when I take the derivative of f times g, I will take the derivative of the first times the second plus the first times derivative of the second. And this is a good example of why I write the product rule as f prime g plus f g prime, because of the fact that I've got this minus that's lumped in right here. It's going to make things a little bit cleaner for me. So let's back up here a bit. We just took the derivative of the y to the third. Now, using the product rule, that's going to give me the derivative of negative x is a negative 1 times the second, which is y squared, okay, plus the first, which is a negative x, right? You say, well, where's the plus? Well, yeah, it's plus a negative x. It's plus the first thing, negative x, times the derivative of the second, which is 2y, but dy dx. Then the derivative of the third term, x cubed, is plus 3x squared. All right, so let's make sure that we did this right. So we've got 3y squared dy dx. The derivative of the first, negative 1, times the second, plus the first times derivative of the second, plus 3 x squared equals 0. 5 derivative of 5 is 0. We got it. Now, since I'm going to evaluate this at a specific point on this curve, I'm going to go ahead and throw in the x and the y. I'm not going to do algebra simplification like I would if I were told to solve for dy dx, right? So I'm not going to move terms over and then factor out the dy dx. No, instead what I'm going to do is plug in a 1 and a 2 for x and y respectively. So this is going to be 3 times 4 dy dx, because y is 2, so 2 squared is 4, minus 1 times 4, y squared would be 4, minus 1, x is 1, times 4, dy dx, plus 3 times 1 equals 0. Okay, going back and double checking. Y is 2. 2 squared is 4. Y is 2. 2 squared is 4. 2 times y is also 4. X is 1. Okay, I don't think I've made any mistakes here. So I've got a 12 dy dx, and I have a negative 4 dy dx. That's going to be 8 dy dx. Here I've got a negative 4 and a positive 3. I believe that would be a negative 1. It looks like dy dx would be equal to a positive 1/8. That would be the slope of the line tangent to the curve at 1, 2. And if this was maybe an open response and you're like, I don't know, does that even make any sense? Right? One of the things that you could do, because Desmos does allow you to graph things implicitly, right? You can't graph that on your TI-84 because you have to have explicit y equals functions. But I can certainly come over here and just see if it even makes sense that the slope would be 1/8. So I'm going to go ahead and graph this curve. And there's the curve. Let's hide that. We're talking at the point 1, 2. So 1, 2 had better be on there. It is. I believe it is. Oh, you know what? I think I had a problem with implicit on here. Does it allow us to even click on it? It doesn't, but there's the point 1, 2 that they're talking about. And, I could see that slope being 1/8. I believe I could. It could be that flat. It's definitely a positive at that point. But yeah, so that gives me some assurance that I think I'm close on that. All right, let's go to the next one. And as I said, just to make a point about this, if this problem were solved for dy dx, so I'll get rid of this. And what if they said they want the function dy dx? Could have done that. But what we would have done, probably would have simplified this a bit. I would have done this 3y squared dy dx minus y squared minus 2xy dy dx. Just cleaning it up a bit, plus 3x squared equals 0. That gives me 4 terms, right? Because I started with 3 terms, but I ended up with 4 because my product rule gave me 2 additional terms. 2 of those 4 terms have dy dx. So I'm going to keep those on the left, move the others to the right. This would become y squared minus 3x squared. And then over here, I would factor out. I'll do it in 2 steps. I probably could do it in 1, but I'm going to factor out the dy dx. That gives me 3y squared minus 2xy. And then I would divide by the parentheses, and I would get y squared minus 3x squared all over 3y squared minus 2 times x times y, like that. And that would be how I would. So you can see I could have done that and then plugged in my point 1, 2 to get my answer of 1/8. But I think it's a little cleaner when you're trying to find the derivative at a specific point to go ahead and just shove that point in and then do the algebra from there. Next question. So Taylor, any questions on that? You can type any questions you have in the chat over there if you would like. All right, let's go to this next one. It says, which of the following is true about the curve x squared minus xy plus y squared equals 3? That's not the same equation, is it? No, it's pretty close, but a different one. Okay, I thought maybe that was the same function. You can see why they call this a curve and not a function, right? This thing is not a function over here that we were working with. It looks like it, yeah, it would certainly fail the vertical line test. So it's not a function, it is a curve. Well, it says which following is true about that at the point 2 comma 1. So before I jump into that, I will survey the answer choices just to see what it is I might be looking for. It's talking about whether the derivative does or does not exist at 2, 1, and whether the tangent at that point is horizontal is or vertical or not. So definitely I'm going to have to find dy dx. So I think what I will do is, in order to answer this question, I am going to solve this for dy dx. So we'll take the derivative on both sides. So let's get to it here. So the derivative on the left-hand side, let me shrink this up just a bit. There we go. All right, this will be 2x. We're going to use the product rule. The derivative of x is -1 times the second. First times the second. So the derivative of y is 1, but then times dy dx. And then plus 2y times dy dx again would be equal to 0. I'm going to do this all in one shot. I'm going to move these two terms over, making y minus 2x. Over here, I'm going to factor out the dy dx. So I'm going to do some mental algebra here. When I factor out that dy dx, that's going to give me 2y minus x, or negative x plus 2y. I'm just reversing the order here. This would be 2y minus x. And I would be dividing by that. And then that would be my, that would give me the slopes of the tangent lines for that curve. Well, let's see what happens when we put the point 1 in. Well, let's evaluate and see what happens. So evaluating this derivative at the point 2 comma 1 gives me 1 minus 2 times 2 on the top, and on the bottom gives me 2 times 1 minus 2. Well, what does that give me, right? That gives me 0 on the bottom, but a non-zero on the top. I've got -3 over 0. That means then that I'm looking at this, because the derivative must not exist right there, because I can't divide by 0. And then I have to choose between, is the tangent line horizontal or vertical? That's an easy choice, because if the tangent line were horizontal, I would not have gotten an undefined answer. I would have gotten 0 up in the numerator, because if the tangent line at that point is horizontal, this dy dx would be equal to 0, because the slope would be 0 of a horizontal line. So I am going with answer D. And as you're sitting at home, you're wondering, I hope I got that right. You want to check it. You want to graph this thing. We will do that and see if indeed we have a vertical tangent line there. If not, then maybe there's a problem with the derivative that we just did. Plus y squared is equal to 3. We are looking for the point 2 comma 1. There you go. So this is looks like it's an ellipse. Yeah, so this is an ellipse that has been rotated, and it just so happens that at the point 2 comma 1, you can see it right there. The tangent line at that point is going to be vertical. That's why the dy dx was -3 over 0. And absolutely, send me more questions. That concludes that part. The first two questions that we got in tonight on AP Calc. Let me see if any more questions came in. We got a few more. All right, let's do this. Here's the next question, AP Calc AB question. This problem here says if e to the x times y minus y squared is equal to e minus 4, then at x equals 1/2 and y equals 2, what's dy dx equal to? All right, let's do this. So we are going to have to take the derivative on both sides, and the derivative on the right side is going to be a 0, right? Because e is a constant and 4 is a constant. So don't get confused and call that e. When you take the derivative, it is going to be 0. So we are taking d dx, the derivative with respect to x on both sides. Well, the derivative of e to the xy, that requires us to use the chain rule. The derivative, let me show you what the rule is for the derivative of exponentials. If you're taking the derivative of e to the u, where u is any function of x, that derivative will be itself e to the u, but times the derivative of the exponent. So when it comes time to me to take the derivative of the exponent, unfortunately, I'm going to have to be using the product rule to do that. So let's see what this looks like. I don't think it's going to be too bad. E to the xy, it's always in its own derivative, exponentials. Now I'm going to multiply that by the product of x times y. So I take the derivative of the first times the second plus the first times derivative of the second. I'll make a comment about that in just a minute. Over here, or the second term, that's a negative 2y times dy dx. Why did I put a 1 and a 1? I don't need to put that there, but I'm putting it there so that if I get further down in the problem and I'm going back and checking my work, it's a place where I showed that I took the derivative of the first and the derivative of the second. So that 1 is representing the derivative of the x of my product rule. Well, I think I will, yeah, I think we're going to go ahead and put in my x and y values straight away. E to the x times y. Well, x times y is 1. So this is an e to the 1/2 times 2, right? That's e to the 1 power. Multiplied by 2 plus 1/2, right? Because x is a 1/2. 1/2 times 1 is 1/2 times dy dx minus 4 dy dx equals 0. I think the only choice I really have here is to go ahead and distribute that e. So I get 3 separate terms. And the 2 terms that have the dy dx, I'll factor the dy dx out, move the other term to the other side. So this will be 2e plus 1/2 e times dy dx minus 4 dy dx equals 0. And remember, let's not forget what we're trying to do here. We are solving for dy dx after we have plugged in that point, which is apparently a point on that curve. If it wasn't, they wouldn't give me those 2 points, right? When they say at x is a half and y is 2, it's because if you plug 1/2 and 2 in for x and y, you're going to get a true equation apparently, but we don't need to check that. That's just, I'm pointing that out. Well, what's going to happen now is I'm going to move the 2e over. And my strategy on this really, class, is I really don't want to be looking at my multiple choice answers at this point. I have a clear vision as to where I need to go, and I want to just cleanly do it and then look at my answers and see what makes sense. I will factor out the dy dx, giving me 1/2 e minus 4. So therefore, my dy dx is going to be negative 2e divided by 1/2 e minus 4. Now, I'm quite sure they're not going to leave a complex fraction in the answer, and they're not. So I'm going to have to simplify that. I'm liking C or D because of the 2 terms, but what I have to do is get rid of that 1/2. I'm going to have to multiply top and bottom by 2, right? That's how you get rid of these. I can't have fractions in my fractions, complex fractions. That'll give me a negative 4e over e minus 8. Now, when we look at those answer choices to match them up, I think there was an 8 minus e. Well, sure, that's not a problem, because if I multiply top and bottom by -1, I'm going to get a match, because that's going to give me a positive 4e, and that'll turn that one around and make it 8 minus e. I multiplied top and bottom by -1. And so there you go. So I'm liking letter C a whole lot right now, and I'm feeling really good. Next, if x cosine y equals pi minus 2y, then what is dy dx? Product rule is coming into play right here. I am taking the derivative on both sides. So the derivative on the left will be the derivative of the first, x. The derivative of x is 1, I should say, at 1 times cosine y plus first times derivative of the second but by the chain rule, I must multiply by dy dx. So the derivative of cosine is negative sine. On the right-hand side, the derivative of pi is 0, and the derivative of negative 2y is negative 2 dy dx. All right, so my strategy is going to be similar here. I'm going to clean this up and solve this before I really start liking or getting rid of any answers. This will be cosine y minus x sine y times dy dx equals negative 2 dy dx. I need to move the cosine y to the right, making it a negative cosine y. I'm going to move the 2 dy dx over here to make it positive, minus x sine y dy dx. And at this point, I can factor out the common dy dx between those two terms on the left, which gives me dy dx 2 minus x sine y equals negative cosine y. I'm going to get my dy dx to be negative cosine y over 2 minus x times sine y. Now we'll go look and see if anything looks like we're close. It looks like my answer choice is going to be A, because definitely they're probably trying to get me to go with C with the plus down here instead of the minus. And if I'm taking this on a test, I mean an actual test, I may go back and make sure I didn't make a sign error, because this really is my answer at this point, right? Because I'm going to multiply top and bottom by negative 1. That's going to give me cosine y over x sine y minus 2. So I'm very confident that I've gotten the answer. But as usual, one of my strategies is looking at similar answers and making sure that those answers aren't the answer, except for a sign error that I might have made. So A, B, and C all look to be pretty similar. So it's worth going back and checking and making sure. One of the most common things maybe that could happen here is someone messing up a sign right here when you take the derivative of the cosine. And either they forget to make it negative sign, or they mess up the sign right here. They forget to bring this minus out here to the front. So at any rate, I like my answer. I'm sticking with it. I hope that helps. Well, I've got more time, so I think I will do a few more unless any questions come in. The stuff that I had planned for tonight was all on quadratics, actually, which probably fits more with Algebra 2, or if somebody was in college algebra, I think they're maybe in the same spot as this. I want to talk about completing the square as a method. I know a lot of the Algebra 2 students, maybe they've just gotten done with complex numbers, and they're going to learn how to do solving quadratic equations by completing the square. I will show a few of those. My pleasure, Taylor. I'm glad you came and asked some very good questions. Those were pretty challenging problems. I hope that helped you. This is a quadratic equation to be solved. And most of you in Algebra 2, you've been learning how to solve quadratic equations, and there's a number of ways that we do it. Maybe the first one that we try is factoring, right? We try to factor our quadratics so that we could, and while we have 0 on one side, so we factor and then set each of those factors equal to 0. There are times when we can use the square root property, where if the quadratic that we're working with doesn't have an x term, like if this term were taken away, well, I could just move the negative 21 to the other side and then square root both sides. And then we would get our solutions pretty straightforward that way. But not all quadratic equations can be factored, right? That's one of the things, is that sometimes our solutions are not what we call rational numbers. They are what we call irrational. And so therefore, there's no way to factor them with integers. By unfoiling, if you want to call it that, by factoring into the product of two binomials. And so there's two other methods that we can use to solving a quadratic. There's actually 3 methods that we could use, and we'll look at maybe all 3 of these. But one of the methods is that if you can't factor, or if you're even not sure that you can factor it, Well, you can do something called completing the square so that you could use the square root property. So I'm going to show you how that works. The other thing that you can do is you could use the quadratic formula. And the quadratic formula is really similar to completing the square in so much as the quadratic formula is derived by someone applying the completing the square method to the general or the standard form of a quadratic. Or you could graph it, right? You could graph the quadratic and look for the x-intercepts. Now, if there are no x-intercepts, then graphing is really not the method to use because you can't see the solutions, right? The solutions are going to be complex numbers, and therefore you're going to have to use some sort of analytical method to find them. But let's take a look at enough examples where I could maybe show you how all of this would work. Well, I am going to solve this quadratic by completing the square, and here is the method. Instead of bringing the -5 over here and leaving 0 and then trying to factor it, what I'm going to do instead is I'm going to move the -21 to the other side by adding 21 on both sides. And then what I'm going to do is I'm going to select a number to put right here that would make that trinomial on the left-hand side a perfect square binomial. And to find that number is pretty easy, especially when you have an even number right here. If it's not an even number, as you're going to see in a minute, it gets a little messy because fractions will be involved. Because what you have to do to get this number that we want to place here is you need to take this coefficient in front of the x, divide it by 2, and square it. And of course, that result that we get is 64. 16 over 2, 8 squared, 64. What I'm going to do is I'm going to place 64, positive 64 right there. Well, if I do that, I need to add 64 to the right-hand side. I can't just arbitrarily change my equation by introducing a positive 64 on just one side. So my equation now becomes this: x squared plus 16x plus 64, and 16 and 64 is 80. Well, what I have now on the left-hand side is a perfect square binomial, meaning that you could now factor it. And when you do factor it, it's going to be, in this case, x plus 8 times x plus 8. Right? What two numbers multiply to be 64, but add to be 16? That would be 8. So this really is x plus 8 squared equals 80. Well, because of the fact that I have this squared binomial on the left, I can then square root both sides. And that will leave me with x plus 8. And over here, I get plus or minus the square root of 80. Well, I do need to simplify the radical. So when you're doing completing the square and even doing quadratic formula, you have to be ready to simplify your radicals. This is 16 times 5. I'm talking about 80 here. That means then that the square root of 16 is 4. So I can pull that out and leave the 5 behind. 16 times 5 is 80. Square root of 16 is 4. So I bring the 4 out to the front. And now I just have one more algebra step and I have my two solutions. I'm going to subtract 8 on both sides, and those are my two solutions. That would mean that solution number 1 is -8 plus 4 root 5. Solution number 2, -8 minus 4 root 5. If we were to take a graphical approach to this, what I would do, a couple of ways I could do this. If you go back to the very original problem and you want to do absolutely no algebra on this at all, when you're trying to solve an equation by graphing, what you can do is graph the left-hand side of the equation, which is x squared plus 16x minus 21, and then graph the right-hand side, which is y equals -5. And we're looking for the intersection points of these two graphs. And if we scroll out, we can see that's one of them. Notice though, and we're not worried about the y values, we're worried about the x values are the solutions. So -0.944 is one of the solutions, and our other solution is -16.944. All right, does that consistent with what we got? I don't know. Let's check it out and see. The two solutions that we arrived at were -8 plus 4 times the square root of 5. Yeah, there's the 0.944, and negative 8 plus 4 square root 5. Oh, minus, sorry, what was the other one? Yeah, negative 16.944. Right. So, but if you want to get, if you do wanted to get them in exact answers, which most of the time you will, the graphing is not really the way to go. So you'd have to use either completing the square or the quadratic formula. I do want to show you one other situation that arises, why it is that you are studying complex numbers as a part of the quadratic unit that you're in, those of you that are in Algebra 2. And that is the idea that sometimes there are no solutions to the quadratic equation because they are complex numbers. Here's what I mean. Even before I want to solve this, I want to graph it and show you something that happens on this function. If we graph this, you can see there's going to be no solutions to this. Remember, if you're solving an equation by graphing, you're graphing the left-hand side and you're graphing the right-hand side, and then you're looking for their intersection points. Well, the right-hand side is the x-axis. Y equals 0 is the x-axis, and this is the parabola. They don't intersect. You can see it never touches the x-axis. So there's no solution to it, but that doesn't, when I say there's no solution, I mean there's no real solution to it. There is what we call a complex solution that involves negative square roots, or it involves our imaginary unit I, and we need to find out what those are. And I can do that by either completing the square, or I can do it by the quadratic formula. I'm going to show you the completing the square method right here. Well, similar to what we did on the previous problem, I'm going to move the constant to the other side, negative 43. I'm going to take half of my middle coefficient, square it. That's 36. Half of 12 is 6. 6 squared is 36. So I add 36 there, but I also must do a plus 36 on the other side. That's going to give me a net of negative 7 over here. This is x plus 6 squared when you factor that. Square rooting both sides, I get plus or minus the square root of negative 7. Well, no such number exists in the real number system because I can't take square roots of negative numbers. But what I can do is I can use, I'm going to go off to the side here and just talk about what does the square root of negative 7 mean. Well, I could call negative 7 times negative 1. And one of the rules of rules of radicals is that multiplication under a radical can be split off into two separate radicals. So I meant to put a negative right here. So the square root of negative 7 is the square root of 7 times negative 1. Splitting it out, it's root 7 times root negative 1. Well, we gave a special name to this. We call that the imaginary unit I. So really what we do is we say the square root of negative 7 is I times the square root of 7. What I'm going to do over here then is I'm going to say, well, this is actually plus or minus I root 7. And then my two answers are found by moving the 6 over as negative 6 plus or minus I root 7. And those are my two complex numbers. Now, what do we mean by complex numbers? Well, the first solution is negative 6 plus I root 7. Solution number 2, negative 6 minus I root 7. Well, complex numbers, as you will learn in this unit, if you haven't covered it already, is that they will include a real portion and they include an imaginary portion. Now, could they include just an imaginary portion? Sure. Could they include just a real portion? Yes. But in this case, we have both real and imaginary as a part of that number. This number is called a complex number. It is made up of both a real and imaginary part. So your teacher will probably tell you that the general form of writing a complex number is A plus B times I. And A and B can be 0. So if you look at all the different ways that you could have a complex number, I could call 5 a complex number. I could call 7I a complex number. I could do 3 minus 2i. It could be root 2 plus root 3 times I. So all of those fit under this umbrella of complex numbers. Now, this really is a real number, but still it is possible to lump it in as being complex with all of the others. And since I've got just a few minutes left, I want to show you a few things about complex numbers. I'm going to show you a pattern on complex numbers. This that I'm going to show you is really not necessary for, this is really what I want right here. Yeah, this is not necessary to know this for quadratics, because when we're dealing with complex numbers, we're dealing with I and not higher powers of I. But this is something that does come in handy when you're taking the ACT. I don't think too much on the SAT, but we need to know powers of I. Well, we know by definition, we have declared I to be the square root of -1. So that's just I, which is I, okay? Now, what is I squared? Well, if you take this equation that defines what I is and you square both sides, you get I squared is equal to that, right? Because you're squaring both sides. Well, that's just equal to -1. So I squared is not an imaginary number. It is -1. Well, I to the third is going to be a negative I, because if you multiply this one on both sides by I, you get I to the third times -1 times I, which is negative I. Lastly, I to the fourth, you could consider that to be I squared times I squared, which is -1 times -1. So it is a positive 1. And what happens is, after you go through that progression from I to the fourth, I -1, negative I 1, well, it repeats itself. I to the fifth, you could call I to the fourth times I, which again is just I, because I to the fourth is 1. I to the sixth is going to be a -1. I to the seventh is going to be negative I. I to the eighth is going to be the number 1. So from time to time on the ACT, they'll ask you about some higher power of I. Well, I do want to show you this on your TI-84. If you're like, I'm not sure what to do about I to the 62nd power, you do have an I button down here. You can pull up I and raise it to the 62nd power. And it's going to tell you it's -1 plus 0I, also known as, of course, -1. Well, if you didn't have a calculator, or you didn't have a TI-4, or you didn't know to do that, what your strategy would be to divide the 62 by 4. Right? If you divide 62 by 4, let's do it over here. 62 divided by 4 is 15.5. So it goes in 15 times. So what is 15 times 4? It's 60. Okay, why did I do that? Because I'm going to write I to the 62nd as follows. I'm going to write it as I to the fourth raised to the 15th times the 2 that are left over, right? Because 15 times 4 is 60. That's I to the 60th, but I need 62 i's. So it's I squared. Well, why did I do this? Because I know what that is, right? I to the fourth is the number 1. 1 to the 15th is 1. So I to the 62nd is the same as I squared, which I know is -1, which is what my calculator told me up here, -1. All right, so that is that. One last thing that I'll show you with regard to these complex numbers that also has application to the ACT, and I would say perhaps to the SAT, and that is rationalizing the denominator of complex numbers. I'll show you 2 examples and then we'll call it a night. Well, I, we know, is the square root of -1, and we don't want square roots in the denominators of our fractions. We do something called rationalize, get rid of those radicals in the denominator. Well, what I'm going to do here, since I just have this one term, I'm going to multiply top and bottom I by I over I. That gives me 10I over 2I squared, but I squared is -1. It's -5I. So this is equivalent to this, but in a simpler form. So very straightforward, multiplying top and bottom by I. That's when I just have a an imaginary part of a complex number. But if I have an entire complex number that has a real and an imaginary part to it, and I need to rationalize it, I have to know that I'm supposed to rationalize that by multiplying top and bottom by the conjugate of that complex number. What's the conjugate? It's when you change the sign in between the two terms. So the conjugate of 5 minus I is 5 plus I. And I would do that on the top and bottom. Well, one thing we know about conjugates is this, that when you multiply conjugates, the outer and inner products will cancel. My outer product here is a 5i. My inner is a negative 5i. So they are going to be inconsequential. All I need to do is multiply the first two terms and the last two terms. 5 times 5 is 25. Negative I times positive I is negative I squared. On the top, I'll go ahead and distribute that negative 2. That would be a negative 10 minus 2i. But anytime that I run into an I squared, I can replace it with negative 1 because we just established that I squared is negative 1. So that's actually 26. This is 10 minus 2i over 25 plus 1, or 26. I'll pull out a 2 and call that 5 minus I. I could have maybe not distributed that. And then that allows me to simplify with a 13. So I can say it's 5 minus I over 13. So these are equivalent complex numbers. This is preferable because I don't have a radical down in the denominator. Well, class, that does it for tonight. I wish all of you a great day tomorrow, your last day off before you return to school. I know tomorrow was a planned day off, and I hope y'all have a good one. And I wish you all the best of luck in the second quarter. I know most of you are starting that second quarter sometime this week. And I look forward to seeing you next week here for another Mr. Rich Q&A. Take care, everybody.